All right, welcome everyone. We're going to keep going exploring exponential functions, and now we're going to be looking at exponential decay. And we kind of looked at this motivating example where we were talking about radioactive decay. And we were investigating just this particular radioactive element that we said had a half-life of 1 day and an initial mass of 1,000 milligrams. And what we saw is that after a few days, we had some data points. And what we saw is that they all fit on this exponential curve. So what we have here is an exponential curve of our usual form. So e to the kx. Now the difference here is we're decaying. So this constant k that we have up in our exponent is going to be negative. With exponential growth, that constant k is positive. With exponential decay, the constant's negative. And using our usual change of base formula to go from exponential functions, we kind of set this up using an exponential function with base 1/2, because what we saw is that going from 1 day to the next, we just multiplied by more and more powers of 1/2. So we could also set this up using base 1/2, perfectly fine. But we're going to be primarily using the natural exponential function, just because the calculus is a little bit easier with that. All right, so let's look through what the general definition is for exponential decay. So we say any quantity is decaying exponentially if at every time t, the rate at which it's decreasing is proportional to the actual quantity itself. So this is the very similar type definition that we saw with exponential growth. So we have our rate of change and we have our quantity. So the derivative describes the rate and the function describes the size of the quantity. And what happens with exponential decay is that these are proportional to each other, so their ratio is equal to some constant k. And what happens, this is basically the same definition that we saw with exponential growth. With one exception, and that is that constant that's up there in the exponent, or the proportionality constant, k, is going to be negative here. And that's because we're decreasing. All right, so this relationship, if we write it as kind of this equation, p prime is equal to k times p, this gives us a differential equation. And this is something that you would see in Calc 2. But the solution for this differential equation is this formula. Very similar formula that we looked at with exponential growth. So let's read through it. Now we're going to phrase this in the form of exponential decay, but it's our p of t, again we can kind of think of this as population, is equal to p of 0 times that exponential factor, e raised to the kt. Now we're going to emphasize that this is the decay formula, and the way we're going to emphasize that is k is negative here. So to really emphasize this, we're going to just rewrite it a little bit. So we're going to write this as p0, so that part will stay the same. And then our exponential factor, we're going to rewrite that k as just negative lambda. And lambda here is going to be positive. So we're taking the negative off of the k, and we're just really stressing that this exponent term is going to be negative. All right, so for exponential decay, and when we're talking about radioactive decay in particular, we're going to let P of T equal the mass of our radioactive element. This is primarily going to be the example we consider when we're talking about exponential decay. So this is going to be the mass of the radioactive element at time t. And then P0, still our kind of our initial population. So this is our starting mass. So again, you can kind of think of this. This is the mass of the radioactive element. You can think of this as like the population of radioactive nuclei in our sample. So you can think of it like a population. But now it's a decaying population. So P0 is still the starting mass, or our initial population at time t equals 0. And then we're calling this constant lambda. This is really going to be the decay constant. And this is a physical quantity. So this really depends on the actual element, the radioactive element that we're considering. So different radioactive elements, they're going to have different decay constants. Now there is kind of an alternate form to this. Rather than using the exponential function, natural exponential function, we could set it up using base 1/2. And in this case, it would be P of T is equal to the initial population. And then we're going to use the exponential function with base 1/2. And it'll be T over capital T, where capital T is the half-life of the radioactive element. So another kind of physical characteristic of the element that we'd be considering. All right, so let's try an example here. We're going to look at example 3. So the decay constant for strontium-90 is given by lambda equal to 0.0244, and time is being measured in years. All right, so we want to know how long it's going to take for some quantity, some starting quantity P0 of strontium-90 to decay to 1/2 its mass. All right, so we want to think about what do we need to find here? Well, it's really asking us, how long is it going to take? So that means we need to figure out T. So it's asking us to figure out the amount of time. So find T, and we want to know how long it's going to take to get down to half our original mass. And we can write that as P of T is equal to 1/2 times P0. So we want to figure out how long it's going to take. So we want to find the time T such that we have half of the mass that we started with. Now the tricky thing here is we're not told how much mass that we start with, but it turns out it doesn't matter. Whether we start with 1,000 milligrams or 10 milligrams, it's going to take the same amount of time for our sample to decay to half the original mass. So it turns out that it really doesn't depend too much on how much material is there to start with. It's going to take the same amount of time for it to decay to half. So what we're going to do is let's write down our exponential decay formula. So P of t, the amount of mass of our radioactive element at time t, is equal to the starting mass times this exponential decay factor, e raised to the negative lambda times t. And what we're going to do is we're going to set this quantity equal to 1/2 times P0 and then solve for t. All right, so let's see what happens. So we're going to take 1/2 times P0, set that equal to our decay formula. So P0 times e to the negative lambda times t. And this gives us an exponential equation that we want to solve for t. And so these exponential equations that we get, it becomes a very similar process for a lot of these exponential growth and decay problems. We're going to have to solve this exponential equation, and it's going to feel like you've done this before, and you really have. So the thing that we can do that might be a little tricky here is, even though we don't know what P0 is, it's just some number. It's some constant. So we can divide it from both sides, and it's going to cancel out. So that's going to give us 1/2 is equal to e raised to the negative lambda times t. And then from here, we know what lambda is based on the fact that we're dealing with strontium-90, and this is just a physical characteristic of that element. So we know lambda. What we don't know is t. And so our usual strategy at this point is to apply natural log to both sides. That's going to get the natural log and the exponential to cancel out. And this will give us the equation natural log of 1/2 is equal to negative lambda times t. And I could have filled in what lambda is at any point here, but I'll save that to the end because it's a decimal. And then the last thing we want to do is divide by negative lambda. Again, this is just a constant. This is just a constant. So don't be thrown by these complicated looking numbers. This is just a number. This is just a number. So we can solve for t. And we get t is equal to natural log of 1/2 divided by negative lambda. And if we fill in what we know lambda is that 0.0244. And if we calculate it out, this is approximately 28. And our units here are years. And what we just found is this is another way to kind of phrase the question here. How long will it take strontium-90 to decay to half of its original mass? Well, we could have asked the same question and worded it as find the half-life of strontium-90. So what we just did, we found that the half-life of strontium-90 is just about 28 years. Whoops. Okay. Now, one little thing. You might be kind of wondering, we have a negative here. How did we end up with a positive value if we're dividing by a negative? Well, the natural log of 1/2, if we just kind of look at this. Now we could simplify this. So natural log of 1/2 is equal to the natural log of 1 minus the natural log of 2. And that's just using our log properties. So whenever we have a fraction inside of a log function, it becomes subtraction. And then the natural log of 1 is just 0. So really, we end up with negative natural log 2 over negative 0.0244. And so the double negative cancel, and we end up with a positive. So not super necessary, but you might be wondering where that extra negative came from so that we could end up with a positive time value here. All right, so that's going to do it. And we'll try some more examples along these lines of radioactive decay. But it's kind of good to try one out before class so we can. And what we're going to be doing next is we're going to look at radioactive carbon-14. And we're going to see how we can use that to kind of do radiocarbon dating. So we'll see you then. Bye-bye.